8.2 Rule of 72. When we want to calculate the increasing rate of something, there is a very useful method called the Rule of 72. So in this video, I want to explain the background and this rule, why we have this rule. Yeah. All right, so first, when we talk about trend in technology, one basic question we want to ask, so that is, what is the increasing rate of transistor density? Based on the Moore's law, there should be some increasing rate, right? Based on the Moore's law, double every 2 years. So here we have this. The transistor density increases by about 35% per year, quadrupling somewhat over 4 years. Quadrupling. So here you can see we use a special word, not doubling, quadrupling. You double twice, then quadrupling in 4 years, right? You double once, you use 2 years. You double twice, you use 4 years. But why you use quadrupling, right? Because most people, they are used to double every 2 years. But here, so this sentence comes from our textbook. But why people use this quadrupling? There is some good reason behind it. So the reason is, in transistor industry, quadrupling has its special significance. So what's that? Quadrupling corresponds to a concept called generation. Generation. The first generation, second generation, third generation. So what's the meaning? All right. Sometimes people want to talk about the current generation of computer chips, for example. Then the next generation of computer chips. How do you define different generations? For human, we can define generations, right? Current generation people after 25 years, next generation people, right? So we have some definition. But in computer industry, that generation, transistor industry, that generation is defined by quadrupling. So the current generation, the density is this much. If after certain years, you get 4 times of that specific transistor density, you move to the next generation. So that's the reason here quadrupling is used related to the generation. All right. Then let's look at the example. So this is a Intel chip technology, 3 different levels. The first one, 22 nanometer technology. 22, we know this 22, the feature size, right? I explained in the previous video, we talked about the feature size. AMD technology, 7 nanometer technology. Here, all right, so Intel, many years ago, they had this 22 nanometer technology. Then, after a few years, they get this 14 nanometer technology. Then, a few years, currently, actually, this 10 nanometer technology, that's their current technology. Most recent technology, 10 nanometer technology. So for these 3 different measures, actually we can compare the transistor density numbers for these 3 different technologies. Here, let's do some simple math. All right, the first one, 22 over 14, approximately 1.57. Simple calculation. Yep. Can we say the transistor density, improved from 22 nm technology to 14 nm technology by this, 57%? Can we say that? No. The answer is not correct. Why? Yeah. Here, remember, we talk about these nanometers. That's the feature size. That's just one dimension. One dimension you improved by that 1.57. But when we talk about density, we should consider the area of the rectangle, right? So we need to consider another dimension. So we need to multiply these two numbers, 1.57 twice, squared. So we need to consider 1.57 squared. That corresponds to the transistor density. Yeah. So the actual number is 1.57 squared, approximately 2.46. So that means from the first technology to the second technology, the transistor density improved more than 2 times, to approximately 2.5 times. That improvement, that big, more than double. Yeah. All right, so that's the first one. Second one, from 14 nanometer technology to 10 nanometer technology. How much improvement in transistor density? 14 over 10, 1.4. Yeah. 1.4 squared, 1.96. Very close to 2. So you can see from 14 nanometer to 10 nanometer, almost double. Transistor density almost double. Yeah. So very close. Yeah. We can treat as double. Yeah. Okay. So you can see, yeah, not necessarily the number double, right? Yeah. From 14 nm to 7 nm, so not double, quadruple, right? 2 squared, 4, quadrupling. Yeah. From 14 nm to 7 nm, quadrupling. Yeah. All right. How long does it take to get that? Here you can see in recent years, the Moore's law is not true anymore, cannot be maintained anymore. Very, very hard. Yeah. Here I use this sentence from an article. So it says, Intel first confirmed issues with its 10 nm technology in July 2015, about 5 years ago. That long. At that time, they developed the 10 nm technology, but not successful. Okay, a lot of problems. Okay, cannot be used in production, in the market. So they delayed the launch of that technology. Delayed. Actually, they delayed many, many times. The first time, second time, third time, fourth time, many, many times. Okay, yeah. So the reason, yeah, here, they gave the reason, and blamed multi-patterning for high defect density. Defect density, another concept. Defect density. Okay, yeah, very, too much density for defects. Yeah. And the low yields, another important concept in computer chip manufacturing. Yeah, the good ratio over all chips produced on a wafer. Yeah, so I show you this picture, the wafer. Yeah. Later in a few videos, I will talk about the detailed information about computer chip manufacturing. Yeah. Here, I just give you a little information. Here, building chips, yeah, manufacturing chips, the process, cut chips from a wafer in, here as a little square. Here, one little tiny square corresponds to one chip, one CPU, one chip, okay? The green one means the good chip. The quality is good, so you can use it in your PC, okay? The one with gray dot, that's the defect one. You have to throw away all those chips with gray dots on it, all bad ones. You have to throw away. So in this example, you can see the total number of dies. So here, one chip, that rectangle, the chip size is a rectangle, but very close to a square, but not an exact square. Close to a square, a rectangle. So it's called a die, right? D-I-E, die. So here, the number of dies on a wafer in this example, 3,252. But many of them are defected, throw away. So how many of those defective dies? 650. That many. 650 dies, chips cannot be used. You have to throw away. So if that ratio, that's called a defect density. If that defect density is very high, then your manufacturing cost is also very high. All right, so then we can take the ratio. In this example, the ratio, the yield, that ratio is the yield. The good dies over total number of dies, that ratio is 80%. Actually, this number is pretty good, 80% manufacturing. Although not as good as 90%. Sometimes some companies can get 90% yield, but still pretty good. All right. Here, the low yield, that number should be much lower than that. Could be as low as 30%. In that case, the technology cannot be used in production. You will lose a lot of money. You can not earn money. You can only lose money. So for that reason, Intel 10 nanometer technology was delayed many times. Only the last year, 2020, near the end of 2020, then that technology was available in the market. You can see this 10 nanometer technology itself already, it was developed more than 5 years. How can you argue the Moore's law still holds, right? Still holds. Cannot. Because after 5 years, the Moore's law already quadrupled, right? Quadrupled. But they stick to 10 nanometer technology for more than 5 years, right? So you can think about Moore's law cannot hold anymore in transistor industry. All right, next, fast calculation for increasing rates. Now we want to do the calculation. Okay, all right. So we start with basic formula for the compound interest. Because this formula is very general, it can be used to calculate transistor density increasing rate. The basic formula is like this. A equals P times parenthesis 1 plus R over N to the NT power. Okay? The meaning, A refers to final amount. Investment amount and other amount, transistor density amount, right? P initial principal balance or initial amount. We can also say initial amount, right? Yeah. R, interest rate. Yeah. Typically, we use the yearly rate, annual rate. Yeah. Then, and the number of compound periods, number of times interest applied per time period, that time period, the year, every year, your interest compounded how many times, right? Quarterly, monthly, daily, right? Yeah, how many times? So that's the N. Yeah. Then T, the number of periods elapsed, right? So that, usually corresponds to number of years. So this is the general formula. Yeah. All right, so our question, what is the increasing rate of transistor density? Yeah. So we use the Moore's law here. So we double every 2 years. Yeah. So you can see this number A means double. Yeah. We set the initial value as 1 here. Okay. Then every 2 years, that N equals 2. Exponent equals 2. Okay. All right. So now we can calculate the increasing rate R easily. Square root of 2 minus 1, 41%. Increasing rate 41%. So very high. But in our previous discussion, we got this 35%. We can see a lot of difference, 6% difference. Yeah. So why is that? Yeah. So I can explain using that special rule. Yeah. All right. So here I want to talk about that rule of 72. Yeah. Here. What's that rule of 72? Yeah. Here, if you want to calculate the increasing rate, use the original formula, compounded interest rate, that formula, it is pretty difficult. Yeah. What I mean is you have to use calculator, right? Calculator to do the calculation. Yeah. But usually, people, in order to use calculator, so they need to do a lot of things. So not very convenient. So then in financial industry, so many people want to get a fast way to do the calculation without using calculator. So they want to find a convenient formula to get the approximate number, not necessarily precise, just a good enough approximation. Yeah. So then someone discovered this rule of 72. What is the rule of 72? This one. Okay? Rule of 72. 72 over interest rate R, the percentage number, interest R, then approximately equal the number of years. How easy it is. Okay? So you can do the mental calculation easily, right? Without using calculator. Yeah. For example, if the interest rate is 8%, how many years do we need to double it? Double the amount, initial amount, investment amount. 72 over 8, 9 years. Is that easy? Right? Yeah. It is much faster than punch keys on calculator, right? Yeah. Another example. If the interest rate is 6%, how many years do you need to double the amount? Investment, suppose you have, right? 6%. 72 over 6, 12. Very fast, right? Yeah. So you have many examples like that. Yeah. All right, so here, regarding this formula, yeah, very famous, convenient formula. Yeah. If you look at the caption here, according to Albert Einstein, compound interest was not only man's greatest invention, but it was also the most powerful force on earth. Here, initially, when you see this, you may feel, Einstein discovered this formula. Actually, it's not. Einstein just said compound interest was very important. Was very important. That's it. Yeah. But Einstein didn't discover this formula. Yeah. Actually, another mathematician, Italian mathematician, discovered this formula. His name is Luca Pacioli. More than 500 years ago. So he was the first one used this rule of 72. Okay? Yeah. Actually, there is another version called a rule of 70. Why? There are two different versions, 72 version and a 70 version. The reason is very simple. The reason we use this number for approximation, we want to get a convenient answer. Sometimes 72 give us convenient answer. Sometimes 70 give us convenient answer. Depends on your interest rate. For example, if your interest rate R equals 10, then the 70 rule of 70 can give you convenient answer. 70 over 10, that's 7 years. Okay, more convenient. If your interest rate is 5, then you'd better use rule of 70 because 70 over 5, 14. More convenient. Better than 72 over 5, right? So mainly, when we choose rule of 70 or 72, based on the convenience, which one can give us, better looking number answer. Okay, all right. Now, for that reason, double every 2 years, right? Here you can see we use rule of 70. 70 divided by 2, 35. Yeah. If you use rule of 72, you will get 36%. Yeah. But only 1% difference. Yeah. But here, why? If we use the original formula, we get 41%. Because these rules, rule of 72 or rule of 70, only when we apply it on a relatively small R number, then it is more accurate. If we apply it on big number, so here the R is a big number. R, 41, 35, that's a pretty big number. Then the error will be bigger. The approximation, approximation error will be much bigger. Okay, yeah. So that's the property of this rule. Yeah. Next, I want to talk about how to derive this formula. It's not easy. How do you get that? Right? So here I want to do some calculation to derive that formula. Yeah. To derive that formula, we start with the original formula. Okay? Yeah. So that's the amount equals, so that compound interest formula. Yeah. Percentage number, so we divide it by 100. Yeah. All right. And that's the annual rate, so we use the year, number of years, n years. Yeah. We should derive this formula, 72 over R, approximately equal to that n. How can we get that? How do we get that? Right? Yeah. Remember that our textbook called a quantitative approach. That means in this course, we need to do a lot of quantitative calculation. Here, let's do some serious calculation here. To do that, we need to use some mathematical tools. Okay? Yeah. The first tool we need to use, natural log. In order to simplify the formula, we need to take the natural log. Can you, after natural log, can you get this expression? Because we want to represent n. Okay? If we take the natural log of both sides, the left-hand side, natural log of 2, right-hand side, exponent n is bring down to the front times natural log 1 plus n r over 100. Okay? Then we do division. So this term, we do division to the left-hand side, so we get this expression. Okay? Yeah. So that's the first step. Then from that expression, next we want to show this expression can be represented approximately in this 72 over r. Approximately. Yeah. So that's our goal. Okay? All right. How to get that? It's not that obvious. If you look at the formula, it's not that obvious. So here we need to use another important mathematical tool. It's called Taylor expansion. Here, the picture here, you see that's an approximation picture. Yeah. So Taylor expansion is used to approximate smooth functions by polynomials. We know polynomials are very simple. Yeah. Some smooth functions could be very complicated. So we want to use polynomials to approximate very complicated smooth functions. Then we can use Taylor expansions. When you use Taylor expansion to do the approximation, just like in this picture, you can see the approximation in this local region is very good. Around some particular point, that part, the approximation is very good. But in other part, not good. So, not good. But we only look at some local approximation. So that's the Taylor expansion. Yeah. Now we want to apply Taylor expansion on this natural log function. Okay. So 1 plus x natural log, its Taylor expansion is in this way. Yeah. That's the arrow term, little o arrow term. Yeah. So that means comparing with x to the fifth, it is very small. Yeah. All right. The arrow term, very small. Okay. Yeah. Here, we can interpret this polynomial approximation in this way. When we use polynomial to approximate natural log function 1 plus x, now, we approximate it in different levels, different steps. The first step, we do one term approximation, only x. We can use x to approximate natural log of 1 plus x. If we do that, then the value we get from x higher than 1 plus it. Yeah, because, we get the values higher than our smooth function. Okay, yeah. So in order to get a better approximation, our second term, we should bring it down. Yeah, because the value is higher than the correct one, so we should correct it. So that's why our second term, we subtract out the second term, n squared over 2. Make correction, bring it down. But after the second term correction, we reduce the amount too much. So it will be smaller than the original function. Then our third term, make another correction, bring it up. So we plus the third term to bring it up. Okay? Then it will be greater than the original function. Then the next term, bring it down again. Okay? So up, down, alternatively, and finally, we make our approximation closer and closer to the original function. Yeah. So that's the meaning of this Taylor expansion. Yeah. So based on that interpretation, we can use the inequality to, to bound the original function. Upper bound x, lower bound x minus x squared over 2. Yeah. Although if you want to prove it, you can use calculus to prove it. But here, we just try to understand the reasoning behind it. Yeah, but here we only use this part. We do not need to use that part. That's enough to use this part. Yeah. We take reciprocal, we have this inequality. 1 over natural log of 1 plus x greater than 1 over x. Okay? After we get this inequality, now we are ready to approximate this original formula. Okay? So we treat this fraction as x. Okay? By this inequality, it's greater than natural log of 2 over x. This is x. Right? This is x. Yeah. Then we simplify it. 100 multiplied to the numerator. Yeah. And we can calculate this number easily. 100 times natural log of 2, using some calculator, we get 69.3. And this number, 69.3, very close to 70, right? Yeah. So that's the reason we have that rule of 70. But 72 is just another convenient version of 70. Convenient sometimes. Yeah. All right. The reason rule of 72 actually is more popular than rule of 70 because we usually have more chances to use rule 72 because 72 equals a times 9, right? Equals 2 cubed times 3 squared. So you can see how many factors do we have from 72? 2, 4, 8, 3, 9, 6, 12, right? 24, right? Yeah. So you can see there are many factors. Okay, so we have many chances to use rule of 72. Yeah. Then let's look at 70. 70 equals 2 times 5 times 7. You have the chances when r equals 2, 5, 7, 10, 14, 35, right? You also have many chances. Yeah. So think about how many factors can we have from 72 and how many factors do we have in 70? You can think about it. Yeah. Later sometime when I have a chance, I will tell you how to calculate it. Okay? All right. So let me just stop here for our second video for this class and we complete part A.